Okay, welcome back to Historical Geology, and I want to wrap up Chapter 17 on the Ice Ages, the Quaternary period, primarily. And one of the things we're going to look at here are the different advances and retreats of the glaciers during this Pleistocene epoch. And the most recent ice age is known as the Wisconsin Ice Age. And then there's a Sangamon interglacial stage, but then before that, there's an Illinoisan, and then pre-Illinoisan A, B, C, and so on. And these used to have different names, but now we find that we're just calling them all different letters for the pre-Illinoisan. But there are 11 stages that predate the Illinoisan, so from A to K. But again, the most recent being the Wisconsin glaciation, with the maximum being about 20,000 years ago, 22,000 years ago. This Illinoisan goes to about maybe 125,000 years ago. In the Sierra Nevada, we see similar glaciations of the alpine glaciers, and the Wisconsin would account for the Tioga glaciation, and those glacier moraines are best seen at Tioga Pass over in Yosemite. But then for the Illinoisan, the best glaciers there, or the moraines we see, are in Tahoe, so we call that the Tahoe glaciation. But then we see episodes that are similar to some of these here, but what we need to understand here is that there were several advances of the glaciers and several retreats of the glacier. So the word we should know is interglacial. So the interglacial would be like the Sangamon interglacial stage, and that's a period where, like today, we're in an interglacial. Whereas a glacial stage would be when the glaciers advance. So interglacials, glaciers retreat. Glacials advance. So there's some scientists that think that we're really not out of the ice ages. We're in an interglacial. We're just waiting for the next glacial to come along. 20,000 years ago, the height of the Wisconsin glaciation, even though sea levels were lower by about 130 to 140 meters, the ice only covered about 30% of landmass. And so what brought this onset? So going from this Paleocene, Eocene thermal maximum that I talked about, the PETM, which had the warmest temperatures, we see that there's a gradual decrease in temperature as we go from this about 55 million year old time period to the present. And there's some periods where there's more cooling, some warming, but there's a general trend of cooling. And that's based on looking at these oxygen isotopes. And the way these oxygen isotopes work is that there are two isotopes of oxygen. There's oxygen 16 and oxygen 18. And oxygen 16 happens to be the lighter isotope. So when there's evaporation of the ocean surface, oxygen 16 is preferentially evaporated. Now let's say that evaporated water, H2O with oxygen 16, ends up on a continent and the climate is colder, and that water ends up being trapped in a glacier and not making it back to the ocean. So as glaciers advance, more and more of this oxygen 16 water is being trapped on land, not being cycled back to the ocean, which means that the oxygen 18 in the ocean becomes more and more concentrated. Or in other words, the oxygen 18 to 16 ratios will increase. So if we look at these numbers, the scale is kind of going backwards. It goes 0, 1, 2, 3, 4. So the higher the number, the more cold it is, the more glacier ice, right? And so here we're seeing these numbers indicating that there's a higher oxygen 18 to 16 isotope ratio, which means the climate is getting cooler. So that's one we would look at for determining glacial stages there. Another thing that really indicates the change from an ice age to our current Holocene climate, because remember, the ice ages, the Pleistocene ends 11,700 years ago, and we really base that number on pollen. And so here's a variety of different pollen. We see pollen from a sunflower, that's number 1 over here, acacia tree, number 2, an oak tree, number 3, white mustard, number 4. We see agave, which is a succulent, number 6 here. And we see a juniper as number 7. So these are different types of pollen grains. And they can tell us something about the vegetation that was around during that time, the spores being sent out. And we find that right around 700 years ago, we changed from this spruce to more of this ash and elm and oak. So indicating that the climate is warming. And that 11,700 years marks the boundary between the Pleistocene and the Holocene epochs. So looking at this diagram here, we're seeing in green are the terminal moraines for the Wisconsin glaciation. So you can see they're pretty extensive. And then all these other colors are either outwash, where all the glacial meltwaters brought silt and gravels or sands out here to the plains. And the word we use is drift. So drift is anything like gravel or silt or sand that's washed away from the glacier. But remember, till and moraine are the actual rocks that the glacier moved and deposited. The outwash was moved by meltwaters, by the water. And then, so we can see these end moraines and glacial lake deposits in here. So these lakes, in fact, these purple glacial lake deposits are really those proglacial lakes we'll talk about in a moment. And when we look at the ice ages and towards the end of the ice ages when the climate was warming, we get different lakes that develop from the melting of glacier ice. Some lakes would develop right next to the glaciers, and those are called the proglacial lakes. Other lakes would develop from the meltwaters going far from the glaciers and collecting in valleys and making pluvial lakes. For example, there was a lake that was almost 100 miles long in Death Valley. That's an example of a pluvial lake. But again, these moraines are marking the maximum extent of the glacial ice during the Wisconsin glaciation. And even in Cape Cod, over here, Nantucket, Martha's Vineyard. So Martha's Vineyard and Nantucket actually mark a terminal moraine for the Wisconsin glaciation. And then as the glaciers retreated, they stalled for a little while here. And the Elizabeth Islands and Cape Cod here mark a recessional moraine. So as these glaciers were moving back. Other things that were happening, we talked about how sea levels were about 130 to 140 meters lower, and that allowed land bridge to develop between Alaska and Siberia. This land, some geologists call Beringia for the Bering Sea. So Beringia was a place where mammals, herds can cross over. Early humans came over, and here's a little depiction of the corridor between ice sheets here after humans crossed over the Beringia land bridge and made it here to colonize North America. Another effect of glaciers melting, because remember, glaciers have mass, there's a weight, and it's just like if you step on a small boat, the boat will sink, and if you and two of your friends step on that same boat, the boat will sink even farther. So the more mass, the thicker the ice, the more the continental crust will sink into the mantle. So now as a glacier melts, that mantle has to rebound. So if you get off the boat should rebound up because the weight is removed. So in some cases, there's been as much as 300 meters, about 1,000 feet of isostatic rebound. And here in Canada, we're seeing about 180, 90, 100 meters of rebound. And most of that rebound we see, that's almost about 1,000 feet, comes in Scandinavia, over in Sweden and Norway. We see that there are fishing villages that were once at sea level, and now they're sitting 600-700 feet above sea level from all that isostatic rebound after the glaciers melted. So here's that thing about those pluvial and proglacial lakes. So these are actually, well, in fact, the Great Salt Lake is a remnant of a much larger pluvial lake called Lake Bonneville. In fact, there's the Bonneville Salt Flats where they do that land speed racing there. We talked about Lake Manly, which is a lake that occupied, the pluvial lake that occupied Death Valley there. Pyramid Lake and Lake Lahontan. So Pyramid Lake is a remnant of a much larger lake that was around Carson City and the Reno area. That was called Lake Lahontan. So that'd be a pluvial lake, which is far from the glaciers. But then the proglacial lakes would be sort of like this Lake Missoula. So there was glacial ice that would come down here, and essentially there was a dam that would eventually, a glacial dam that eventually would rupture occasionally and allow this Lake Missoula to drain, and also this lake column to drain, and they would make there's these huge erosional features that are seen throughout this part of Washington State, and they're called the scablands. and they indicate scouring of meltwaters, ginormous floods where this entire lake was probably drained within a couple of days out down the Columbia River. So huge scablands related to this breaking or failing of these ice dams as the glaciers were retreating here. So those are the scablands that you find in Washington State. So again, looking back at Lake Bonneville, it's a large pluvial lake in Utah, Nevada, southern Idaho. And today, Lake Bonneville, we have the salt flats as the lake dried up. And also we mentioned that the Great Salt Lake is a remnant of that once larger Lake Bonneville. And also your book mentions that Lake Bonneville also flooded eastern Idaho, and its flood was about 30 times smaller than that of the largest Lake Missoula flood. So not as extensive, but still we had some flooding down here in Lake Bonneville as well. And then in the last video, I talked a little bit about what could be causing the glaciations, and they're not that common. There's really a couple of episodes that come to mind, at least in this class that we talked about. We talked about the ice house Earth, and the snowball Earth. And so how in the Neoproterozoic, we had those two glaciations around 700 million years ago to about 630 million years ago. And so those are marking the Neoproterozoic glaciations. And then we had glaciations as Gondwana moved over the South Pole in the late Paleozoic. And then the next time we're really seeing them are here in the Pleistocene epoch, where we're seeing temperatures change. So there's really no explanation for these Pleistocene glaciations that completely satisfy all the data. Could it be plate movement, changes in ocean circulation patterns, a decrease in atmospheric CO2? Some people point out that because the Himalayas were beginning to uplift around 40 million years ago, a lot of chemical weathering was occurring. And remember, chemical weathering removes carbon dioxide from the atmosphere, so that might have contributed a little bit to the Cenozoic cooling. And we do find that around 40 million years ago, we begin to develop the Antarctic ice sheet, or the glaciers over Antarctica. So there might be a little bit that goes along with that. We also talked about the Milankovitch cycles in the last lecture, and how the way Earth orbits the sun and how the solar system goes around the Milky Way galaxy. You can have periods of eccentricity or obliquity, but really what I want you to get out of this is that these cycles do explain the timing, maybe not the extent of the glaciation, but they do help explain the timing of the different glaciation events.